Hello, everyone. I am Luiz Hespanha. I'm here with Flavio, Brazil. We work in a company that has more than 1,000 microservices written in Clojure, so using the JVM, and these services are running in Kubernetes clusters. Unfortunately, Clojure is not so popular, but JVM and Kubernetes are common tools used by several companies, and it brings some challenges that we'll talk today during this presentation. To start, we'll talk a little bit about Nubank and the payment market in Brazil to give a better understanding of the size of the problem. People in the US know Nubank mainly because we acquired Cognitect, the company behind Clojure and Datomic, but Nubank is much more than it. Nubank is a mobile-first fintech founded in 2013 in Brazil with the mission of fighting the complexity and charging no fees. Our first product was a credit card in 2014, and since then, we are seeing hyper growth in the number of customers, and in July of this year, we reached 85 million customers. Now, we are also operating in Mexico and Colombia. Thanks to this growth, Nubank in 10 years went from a small startup to the fourth biggest bank in Brazil. Another exciting data is that 46% of adult Brazilian population is a Nubank customer now, almost 1 in every 2 people. When you are in a hyper-growth company, you are constantly challenged with scaling issues. And to make things worse, we had the perfect storm. In the end of 2020, the Brazilian Central Bank launched Pix. Pix is a real-time 24/7 payment platform. You can use your Pix key, that can be an email, cell phone numbers, social ID, a random key, or you can just scan a QR code to transfer money and payments instantly at any time. Pix was a huge success in Brazil and developed a very fast adoption. In July of this year, Pix reached almost 4 billion transactions in the month. And now, Pix is essential for people's day-to-day. Like in Brazil, people don't say anymore, make a payment, people say, make a Pix. So if Pix is not working, it's a huge problem. And especially during the payday in Brazil, in the beginning of each month, we are facing several incidents with Pix. It was making our customers unhappy because they have money in their checking accounts, but they couldn't use it, so they were unhappy with the reason. And it was also causing reputational damage for us, since even the press was talking about the problem. Also, since Nubank is one of the largest banks in Brazil, when we are out, all the Pix ecosystem suffers, generating also regulatory concerns from Brazilian Central Bank.
So thank you, Hespanha. To understand the problem, we decided to start inspecting systems to understand where the instability was coming from. The first thing that we observed is what we called the crash resolution paradox. It was a strange situation. We would see a system running, for example, for 3 days here, and even during the peak hours of the day, it would reach only 4% of the CPU usage. But then when we got to the payday and the load spike that came with it, we would see the system fading because of CPU usage. So the system would go top 100% CPU usage, and we would sometimes have to manually, for example, restart the system. And the latencies would skyrocket, and many systems would become unresponsive. And the resolution for this kind of crash was actually increasing the CPU resources of the system. So it's a strange situation, right? How come a system that can't use its CPU quota efficiently fail because of CPU usage when there's a load spike? The second observation was a couple of crashes that escalated to cluster-wide instability. In those crashes, we saw some nodes in Kubernetes starting to get saturated. So basically, they didn't have enough CPU resources to handle the workloads, and threads were queuing in the scheduler, Linux scheduler. In most of the cases, we saw that a few problematic systems were consuming all CPU resources of the nodes. And this pattern of instability spread to multiple nodes. So we got our whole cluster actually in an unhealthy state, and several systems were failing in that case. And these are strange patterns, right? These are strange symptoms. And they are actually symptoms of a bottleneck. The universal scalability law explains that when you are containing for a resource, when you have the CPU, for example, at 100%, there is a natural degradation of the efficiency of the system. But then when you start having effects of coherence, that is basically coordination between threads, for example, for CPU throttling, to enforce quota, there is normally a sharp drop in efficiency that explains what we were seeing with our systems. And we were seeing also in the trends of the metrics we had. So the blue line there is the CPU usage median across the day, and the bars are the cost of the system. So the median CPU usage was dropping over time, and the cost was growing higher than the loads that we had. So basically, we had hit a bottleneck, and that bottleneck was making our systems less efficient over time. So we set two main goals to solve this problem. The first one is, even if the systems get overloaded, they should remain functional. They shouldn't be failing because they can't handle the load. And the second goal is that problematic systems could not affect the performance of other systems, right? So these were the two things that we were after when we started this journey.
Well, the path to our goals wasn't trivial, since there is a lot of conflicting information on the internet. When running several containers inside the same machine, Linux has some mechanisms to guarantee the CPU isolation to avoid that a container interfering in all the others. Also, in the Kubernetes world, you can use the CPU requests and CPU limits to define how much CPU a container can use. The CPU requests in Kubernetes becomes the CPU shares configuration, and the CPU limits becomes the CPU quota. The CPU request acts as a soft limit. The container you use, you have at least that amount of CPU to use. And the CPU limit acts as a hard limit. That's the maximum CPU that the container will be allowed to use. CPU requests works with prioritization when all CPUs are busy. While there is free CPU in the node, containers can use more CPU than requested without limitation. Only when all CPUs are busy, it prioritizes the execution to guarantee that each container use at least the CPU requested. On the other hand, the CPU quota is enforced even if the node has more CPU available. And the CPU request isn't able to prevent node saturation, as it only acts when containers are contending for CPU. CPU limits can, in most of the cases, avoid saturation. It's a quota and not a concurrency limit, but it's generally enough. This CPU quota mechanism can show some weird scenarios. In this case, for example, we have a system with a low average CPU usage. People can look at this graph and even consider the system is over-provisioned. And we don't expect any CPU throttling in this case. When we are talking about CPU throttling, it's the case like when Linux stops all the threads of your application and you can run anything during this period. And surprising, we have CPU throttling even with a very low average CPU. To understand why, we need to understand how CPU throttling works.
So we have this example. It's a fictitious example of a container having 4 cores of CODA. And we are distributing the CPU usage in these squares that are basically 20 milliseconds of CPU usage. And we have a few periods in the example. The first one is basically the application running with 4 threads or 4 cores active throughout that period. And it's basically within the CODA, right? So it's using its full CODA. There's no CPU throttling, no problems. The second period, actually, the load goes down, and the application isn't able to use the full CPU CODA. And an important factor here is that the CPU usage, the CPU CODA that's not used cannot be reused later. The application loses that CPU that wasn't used in the period. And then we get to the point that is interesting. That is, the application has a load spike. It starts using many cores in parallel, and then it consumes the CPU quota very quickly, right? So if the application has too many threads running, it's going to basically consume all the resources that's allocated to it very quickly. And at this point, the CPU is going to be throttled. And as Hespanha mentioned, when it's throttled, it's actually pausing the entire container, even things that are, for example, GC or more low-level Linux operations. On the fourth period, there is an interesting pattern that we see that is, in the previous periods, the application was paused for a while. So you have some backlog of work to do, right? So the application is going to start processing that backlog. And if it doesn't have a good concurrency limit, it's going to consume all the quota again very quickly and then get throttled again. So it's something that accumulates, right? It's a pattern that introduces a lot of issues into the system. And then for the last periods, we have like just the load going down and then some throttling still. It's very important to keep in mind that when the CPU throttling happens, it's pausing not only, for example, the request handling HTTP requests or everything, but it's also pausing, for example, garbage collection in the JVM. It's pausing health checks, right? So you can start having lots of problems, and that's a lot of the factors that ended up producing the instability in our systems.
So it's clear that CPU throttling is a huge problem, but how to solve it, how to avoid CPU throttling? There are currently too many current schools of thought about this problem. The first one is just disable limits. It's a common recommendation to avoid setting the limits configuration and allow systems to use the CPU resources freely until a node becomes saturated, at which point the CPU request will be enforced. The other school is CPU pinning is the one true way. Some people recommend do not use CPU requests and limits and allocate specific CPUs to specific containers via CPU pinning. But both these solutions have some limitations. When disable limits, for example, how can we prevent problematic systems from consuming all CPU resources of a node and affect performance of collocated systems? Also, reasoning about the performance of systems can become very challenging since it becomes environment dependent. A system might behave well if the node has free CPU to be used, but it will perform poorly in a node with no CPU to borrow. CPU pinning also has some important downsides. What about small systems with fractional quotas? We have a large number of systems, and many of them use very small quotas, sometimes even less than a core. So the lack of fractional quota when pinning could increase the cost of all the Kubernetes clusters. Also, it do not allow, there is no possibility of bursts, and it adds pressure to Kubernetes scheduling, like the combination problem that Kubernetes needs to do to allocate pods to nodes becomes much more complex with the additional CPU pinning dimension. But more importantly, we felt that these approaches weren't proper answers for our problems. The real question is, what are these approaches hiding?
So this problem is actually connected to a common problem in software engineering, that is the danger of averages. So almost a decade ago, Giltin published this blog post where he has a definition of average. That is a random number that falls somewhere between the maximum and half the median, most often used to ignore reality, right? And today, in our industry, we can say that like when we show a graph like this that is just an average of latency, people already know this is not something good. This is not a good way of measuring latency. And today we use percentiles for that, right? So we see the distribution of latencies to understand how the system is actually behaving. But then we go to how we measure CPU usage again. And if you pay attention, it's actually an average. So what's happening there? We have observability systems like Prometheus, for example, doing scraping of metrics every interval, for example, 1 minute. Here, that is a common interval. And what is it's scraping? It's basically 3 counters for CPU usage. So we have only a snapshot every minute of the CPU usage. So when we go back to that example where we have low CPU usage with CPU throttling, can we really say that the system is not hitting its quota, right? We have only a snapshot and an average over minutes. Can the system maybe be using more CPU than the resources during that 1 minute window? And we ask again, what is this hiding, right? So the actual thing is the CPU average is a lie, right? It doesn't represent how the system is using its CPU resources. It doesn't show, for example, these patterns of variation that can generate CPU throttling. And today, we have very low visibility in our industry because we use average for CPU utilization. So to solve that, we decided to develop a new solution that is basically having fine-grained CPU metrics. Initially, we just built something very quickly with a terminal dashboard. There is this project called Sampler. It's a great project to build terminal dashboards. And we integrated it with JMX to connect to a pod and then observe the CPU usage in real time. So here you can see that what we were seeing before, the 4%, is just a lie, right? This is the actual behavior of the system. Sometimes it has a load spike on CPU, sometimes it's mostly idle, sometimes there's a spike where it sustains for a while. So this is really, really interesting information, right? This is valuable information to optimize the systems. We eventually also started compiling these metrics in a histogram. So we basically measure every 100 milliseconds, and then we provide a histogram for Prometheus to scrape every minute. So we can see how the CPU usage is varying within each 1 minute window that's of the scraping, right? And this gives like a lot of visibility over the problem. But then the next big question is, how can we make systems behave? What are the main factors that make them vary the CPU usage? And our answer was creating a new solution to control the concurrency of applications.
We developed a solution to automatically control the concurrency of systems in a way that allows them to avoid major degradation. It's an adaptive threading model that constantly tunes the systems to avoid CPU throttling. We called our project Navu, inspired by the TechSpence show, and there are three main things Navu does. First one, fine gradient perf metrics. Like you can't improve what you don't measure. So we added several new metrics like percentiles of CPU usage, percentiles of throttling, the time delay to schedule threads, a bunch of new metrics that give us a better understanding of what was happening with the systems. The second is an adaptive concurrency. No more manual thread pool tuning. It's really hard to define the size of a thread pool should have, since it can change a lot depending on the workload. Like, if you have a CPU-intensive flow, the behavior will be completely different of a flow with too much I/O and thread blocking. That's why we believe that an adaptive concurrency solution is important. And the third point is reactive pressure. Reject work above the system's capacity. With a queue unbounded, if you are in a system with a huge load, your queue can grow very fast, putting pressure in the memory and in the GC, putting pressure in the GC and in auto application. The first thing to Navu works, Navu needs to control the concurrency. We tried different approach to implement this. Navu controls the concurrency, it needs a mechanism to detect degradation in a service. We tried different approaches to implement this detection mechanism. Our first try in V0 was check all the things, and what does that mean? We are checking CPU usage, CPU throttle percentage, memory, everything trying to avoid degradation. After some experiments, we saw that this mechanism was working well to control instability, but it was too strict, as it didn't accept any throttling, so it was hurting the performance for some systems. Then we added the heartbeat mode. This mode was inspired in the JRecap solution created by Guillotine. And basically, it starts a new thread that runs a while loop with a sleep call inside. It forces the scheduler to put our thread to run immediately after they sleep. So we can measure this time, and we can identify delays in the scheduler, which indicates degradation. The good part of this solution is that it also detects GC pauses, JVM safe points, and also allocation stalls. With this solution, we had a better performance results without compromising stability. That was our main focus.
So then, once we had these mechanisms to observe the degradation of scheduling, we had to introduce a way of controlling the concurrency of the system. So traditionally, in a JVM application, we have executors using the Linux scheduler directly, right? So you are starting threads, and you are scheduling those threads directly on the Linux scheduler. And we use the old technique of introducing indirection. So we added Navu in the middle, so executors are redirected to Navu, and then we can, in Navu, control how much concurrency is available to the system. There is like some complexity around how to redirect to those thread pools. We are not going to be able to go in details. But how we control the concurrency is actually very simple. If you have the system having degradation, it means that it's hitting a bottleneck. So you have, for example, too many threads and you are hitting CPU throttling. Or you have too many threads, you're processing and allocating too much memory, and you're having allocation stalls, RGC pauses, right? So you're basically, by reducing the concurrency, Navu is reducing the capacity of the system, so it can avoid any bottleneck that might be happening at that moment. And it's something that's happening all the time. So it's not something that we process and then apply to the systems. It's something that's running with the system all the time to adapt to the workloads. And then if the system the threads are being scheduled reliably, there is no degradation, then Navu allows the system to use more concurrency if necessary. And for this mechanism, we had two main challenges. The first one is reaction time. For example, if you have a system that's running and you have, for example, GC execution that is going to consume some CPU in parallel concurrently to the application, it might need to reduce the concurrency of the application at that point, right? So it needs to be something that reacts fast to these kind of changes in workloads. Or if you have thread blocking and an external system has a higher latency, you have to quickly react to allow more threads if necessary. And the other challenge is the stability of the control loop. If you have a control loop that's always changing threads all the time, you can hurt the performance of the system, right? So because you are always introducing noise in the execution. And for these two problems, the first one we solved by using something simple that is start with small changes, but if they are not effective, it quickly escalates using exponential steps. So it adapts very quickly, but in a stable manner, right? The second solution was basically for the control loop to be stable, we introduced a meta-stable state. That is that the control loop detects that the application is close to its limits, but it's not degraded to a point that we need to act. So the control loop basically keeps the system as it is without making changes. So it reaches a stable point at that, a certain moment.
So here we have some examples of workloads, and Navu adapts the number of threads. In this case, Navu is adapting the number of threads to a load with low CPU usage and thread blocking. So as the load increases, Navu can also increase the number of threads to avoid queuing. And it's totally fine because everything is under control. Like there is no CPU throttling, the heartbeat delay to get the delays in schedule is okay, the CPU usage is under control. So it's totally fine to Navu increase the number of threads to be able to handle the load that is increasing too. Here in this case, for example, it's not easy to see, but Navu is already with 200 threads and it's totally fine. In this another example, Navu is adapting the number of threads to a CPU-intensive load, so the threads need to really use the CPU. So in this case, Navu needs to decrease the number of threads because the service is suffering with CPU throttling, and also there is some delay to schedule the threads. And also, this example shows the other thing that Navu does that's been rejecting some of the tasks that's arriving to the service. So in this case, 5% of the new tasks are being rejected, so Navu can maintain the service stable. Because the main focus here is try to avoid the service crashes. Like if you had a hard-coded number of threads, if you try to use all these threads, the service can crash. So Navu is automatically adapting for it. So in this case, for example, Navu is using 24 threads. And another aspect that's very important that the other things like GC, for example, if there is a lot of garbage in the application, the GC threads also use CPU. And so Navu is also able to detect this increase of tasks, GC threads running, and also reduce the number of threads to avoid CPU throttling. And when GC is over, Navu can increase the number of threads again, everything automatically. Now we will show some results. We will show 3 cases with 3 different impacts Navu have in the service at Nubank. The first case is an improvement in the stability. It's the social service. It's a service that is it's a key service for the PIX flow. And after Navu adoption, you can see a significant improvement in the service stability. Like before the stability was decreasing month after month, the service was suffering a lot. And we can see that now the trend reverted and the stability is increasing now month after month. The second case is amazing. It's an improvement in the latency of a service called magnitude. And this service was suffering a lot with throttling before Navu because it was using too many threads. So it was suffering with CPU throttling. After the Navu adoption and the concurrency control to avoid degradation, we saw a significant improvement in the latency. And the third case was cost reduction improvement. It's in the Storm Shield, another key service for the PIX flow. This service was very unstable before Navu, and to try to mitigate it, the team increased the service resources a lot. After we added Navu and made the service stable, we could remove the over-provisioning of the service without compromising the stability. Now we'll talk a little bit about the next steps post-Navu adoption and what are our plannings to the future of the project. With Navu enabled in the service at Nubank, we can identify performance bottlenecks more clearly. To give an example of it, in this case, using the CPU percentiles metric, we identify peaks in the P99 CPU usage in a service, and we correlated it with some specific endpoint calls with high latencies. Looking at the code, we saw that these endpoints were using a closure macro in production that should be used only in development environments that were very expensive. So once the fix was deployed, a large drop in the P90 and P99 CPU usage was observed. It's interesting that the average CPU usage continues exactly the same. So without these new metrics Navu added, we couldn't even measure the improvement. This case was a mistake of the engineer that implemented these endpoints. But like this mistake was in production for months in this service. That's a very important service. And only when we added the Navu, we are able to see it easily and fix it. And there are several cases like this one, with people from other teams sharing with us that they use Navu to identify performance bottlenecks.
So now that Navu is rolled out to most services and the critical ones at Nubank, we are focusing on building the next iteration of the project. And we have three main focuses. The first one is lower overhead. So we have systems that have quotas, for example, of half a core. And the metric collection and the control loop becomes too much overhead for this kind of system. So we are focusing on building solutions to avoid these overheads and support this kind of workloads. The second focus is Loom integration. Navu is a key point where we can easily switch executors from native thread blocking to virtual threads. So it's very convenient for us to do the migration to Loom. And something that's very important, sometimes there's some confusion because people confuse the need for something like Navu versus green threads, right? It's actually, these are orthogonal problems. Even systems that are fully asynchronous, they benefit from Navu's features. For example, we have systems that are on top of closures core async, and they still benefit from the thread pool tuning, and they still benefit from, for example, the load shedding when necessary. And the third focus is preparing for open source. We hoped maybe to have open source by the event today, but we couldn't. But we are focusing on building and preparing for open source. So keep an eye for announcements from Nubank's engineering if you are interested. Just to finalize, before finalizing, we want to highlight something very important. So the work to stabilize PIX and the Nubank's platform as a whole was like a collaboration of multiple teams, right? So we had teams rewriting systems, we have teams migrating to different databases, we have like optimizations of our own datomic database. So there's like lots of work of many teams, right? And Navu's adoption was basically just one slice of this work. So it's not everything, right? And now we have what we can say is payday sanity, so the system works when we get to the payday. We have to knock on wood to say that, right, because it's hard, but it's really something that changes how the company is able to focus on building solutions for the users, right, instead of dealing with systems problems. So it's really a breakthrough for us. In August, for example, we had 99.9 availability for the PIX transactions. That is really a huge breakthrough for us. So that's all we had for today. We have our Twitter handles there if you want to check it out. And if you have any questions, we are going to be around. Feel free to reach out. And we are especially interested if you're working in the same domain, the same kind of problems, please come talk to us so we can exchange experiences as well. So that's all. Thank you.